my name is James Kolaoli Adele, and this is your favorite YouTube channel that is going to be talking about tech. And of course, you are on with Tech with AY. Today, we are going to be dealing with how to use about 7 different machine learning algorithms to be able to predict the existence or the non-existence of heart disease in a client. Or of course, we're going to be using 900. We're going to be using this cargo website. This cargo, we're going to be getting our data sets from this cargo website, and of course, it's actually here. All right, this is heart disease data set. We're going to be getting our data set from this website by downloading it into the directory that we are using for our work here. All right, and of course, the ID that I'm going to be using is Jupyter Notebook, which I got from Anaconda uh, software. So you can download this Anaconda from the website, and then of course you can get your Jupyter Notebook right from there. All right, you can launch your Jupyter Notebook and you can follow me. Of course, if you are okay with it, you can also use Visual Studio Code, all right, as your ID, all right, to be able to run your commands. All right, it is going to be very, very interesting because I'm going to be using 7 different machine learning algorithms, all right, from support vector machine to decision tree based models, and of course, to deep learning algorithm. All right, to be able, and these are done in order to be able to get the best models that is going to give me the best performance or the best accuracy. All right, so of course, I'm going to be using several metrics like the classification report, and I'm also going to be using AUC, and on each of the model, I'm going to be getting what is called the feature importance, and this feature importance helps us to be able to explain to the people or to the stakeholders the importance or the impact of the features on each of or on the impact of the features on in predicting or in getting the results that we are actually talking about. So we want to know, and this is actually for transparency and for accountability in our models. We want to be able to explain to stakeholders the impact of the features on a target variable. Of course, in this data set, we are going to be having 12 different features, which one of them is going to be the target variable or the label. And we're going to have 11 independent variables, all right, which we're going to be using for training our data. And the independent variable is when we talk about the independent variables, we're talking about the features like age, sex, chest pain, and of course, this is the target variable, which is the heart disease. All right, and of course, we are going to be so these are the things that we are going to be doing. All right, and we know that it's actually very, very important and imperative to be able to quickly determine the possibility of a heart disease in a patient. And of course, why do we need to do that? By coming to this place, and we can see here that cardiovascular disease, which is called heart disease, are the leading cause of disease globally. An estimated 17.9 million people died from CVDs in 2019 alone, representing 32% of all global death. Right, of this death, 85% were due to heart attack and stroke. So this actually is very, very important. It is important to be able to find solutions to actually be able to predict the occurrence of heart disease in the patients, and this will drastically help to reduce the amount of death or in the population. And it's actually very, very important to be able to build something that can actually uh, have a significant impact in the life of the people. All right, and before we actually start, of course, we're going to be doing some installations. We're going to be installing LightGBM, which is actually one of the models that we're going to be using in this study. Of course, we're going to be also installing CatBoost categorical boost classifier. These are the classifiers, and then of course we're going to be importing we're going to start by importing the warnings, and of course we're going to be importing numpys and pandas. All right, which we're going to be using for manipulating our data sets. All right, to be able to create a manipulate data frame. All right, then of course this is the visualization. So we're going to be using matplotlib and plotly. All right, plotly express or matplotlib, and then cbono as well. All right, these are the visualization that we're going to be using in our data set, of course, which we are importing here. The pre-processing libraries, the machine learning libraries, and of course evaluation. And these are the libraries that we're going to be using. all right, in terms in solving the problems in doing our work here. Of course, we're going to start from loading the data set. Of course, like I said, you download your data set from Cargo, and it's going to be at disease.csv. So PD is equal to read dot, yeah, df is equal to pd.read underscore csv. All right, and this is how we can actually use. You can use dot head or you can use dot tail. All right, if you say pd.head, it's going to give you the first five samples in your data set. All right, of course, if you say pd.tail, all right, by coming to this place and say df.tail, all right, it's going to give you five, uh, the last five samples, the last five samples in your data set. I don't want to use the word row or columns because no, it is actually not professional. So the samples and the features are what we actually use here. Data preparation. All right, to get information about your data set, you can use df.info, which is actually been done here. It tells you that you have 918 non-null. So all our data set doesn't have, none of them actually has null data set. So we don't need to have any issues with the data set because all of them are actually filled with numbers. So we have df.shape. This actually gives us the shape of the data set, and of course we have 918 samples, and we have 12 features, including the target variable, which is the heart disease. And the heart disease contains 0 and 1. 0 means the absence of heart disease, and 1 means the presence of heart disease. So we have a df.null to check the null numbers in our features, which actually is actually completely 0. So this code snippet simply, loop through the data set, loop through the data frame to be able to get the unique numbers on all, considering each of the features. And we can see here our target variable only has 2, which is 0s and 1. And these are the unique features. So this tells you that cholesterol actually has the largest number. And of course, in the data set, we have the categorical features and the numeric features. So we're still going to be talking about how we can actually convert them or like encode them to be able to let them pass into the pipeline for our data, for our model to be able to predict them. So this is the describe. All right, these are the things. These are the things that we can use to be able to manipulate a data frame in these Jupyter Notebook. We have duplicates to get the duplicated values. All right. We can actually try to eliminate duplicated values if we want, but right now there's no duplicated values. Now, these are the data visualizations, of course. We can actually use matplotlib, like I said. We can use Seaborns. Then we can also use Plotly Express to be able it's actually very imperative for us to be able to know how to do these visualizations. It helps us to explain to get some insight in our data set and to be able to do a lot of things in our data set. So these are just some of the things. This is the D types. This shows you the data types. We have object and we have integer 64. We have float 64. Of course, these are actually there. Then we are actually trying to get these use this to be able to visualize the sex. Of course, we try here. Yeah, we're trying to separate. We're going to split our data set from into categorical and numerical variables, and then to be able to check some things there. All right, now here, of course, we can see here, this is check if the feature is categorical or continuous or numerical. Or if it is categorical, we're going to use this histogram, and if it is numerical, we're going to use the box plot to be able to explain for it to be able to compare with the target variable or the label, and the target variable is heart disease. So we are trying to do this comparison between each of the features and the target variable, and these are actually what we are seeing here. All right, it tells you that the male has significantly high chance of getting from this data set than compared to the female. All right, and why we are trying not to be very biased in our data set, we're not actually going to use these sex as the main predictor. All right, so that we will not be able to bias because we have some this sex is actually a very very sensitive features. All right, and it's a protected features, so we are not going to be using that. But like I said, this is just like we're trying to see get some insight into data sets. All right, and we can see here that we have this heart disease, which is no heart disease, and red contains heart disease, and so we can see here that there is a huge number of prevalence of disease among these male and compared to this female in terms of the sex. Of course, this is the chest pain type you can see here. This is 1, this is 0. Chest pain type of ASY is significantly higher than every other ones. So we're trying to see if we can actually get some insight in our data set to be able to know what's actually going on. So it's very, very imperative for us to be able to use exploit analysis to get some insight in our data set. And of course, you can actually see some of the very exciting things, features here. And it is actually very, very good. You can actually get go into the some of these documentations on the website to be able to get how you can get more insight into your data set than this one. All right, so we have what is called the correlation matrix, and of course, part of the correlation matrix is encoding. Encoding is a process of converting categorical data into numerical format that can be used for machine learning algorithm. Of course, if you want to do deep learning, you cannot just pass your data set into and start to run it with a deep learning algorithm or with a pre-trained algorithm. What you need to do is first you need to change the images, maybe .png file or .jpg file. You need to change into numpy array, and then you can actually be able to pass it into the neural networks, and of course the back propagation and the forward propagation before you can be able to get into predicting what is actually happening in your data sets, then in your images. All right, so it's actually very imperative, like I said, for you to convert all categorical data into numerical data so that you can be able to pass it into the machine learning algorithm. The machine doesn't understand all the words, the characters. They understand zeros and ones, and they understand the numbers, and that's what we're trying to do here. So we're trying to print the unique values. Of course, this is the unique values for sex is MF and the unique. So one of the ways by which you can use to without using apart from using one not encoding, we can use this replacement. You can replace them, and of course that can actually be used in terms of the encoding. And this is actually very, very simple. Instead of one auto encoding, so we've been able to transform our data into zeros and ones by and two and three. All right, by using this method. Of course, we're also going to be showing the correlation matrix. This actually correlation matrix is actually very important for us to be able to know, the correlation between each of the features to the target variable or to the label, and also each of the features to each other. If you have a feature that has a significantly higher correlation with the target variable, it is actually very imperative for us to be able to remove them. All right, so that it will not affect the performance of our model. And of course, if each of the features has significantly high correlation with each other, it's also imperative for us to drop them because they are likely going to have a significant adverse effect on the performance of the model. All right, you can see here that the one that has the significantly higher compared to our disease is ST slope, which is 0.5 now, which is actually very good. At least we don't have anyone that have like 0.9 or 1.0. All right, so this is the future engineering. In feature engineering, we're going to be dealing with what is called dimensionality reduction. And we can actually see here that we have some features that actually have significantly lower correlation with the target variable. And of course, we have resting BP, like I said, I guess, and we have resting ECG. And here we're going to be dropping them. And the reason why we are dropping them is that by the time we are creating like a user interface, it is going to be too many, by the time we are loading the data set. So we actually have to, in order to also improve the model efficiency and reduce overfitting and enhance interpretability, we need to do what is called dimensionality reduction, and that is how we have been able to reduce and drop two features in our data sets. All right, so we have um, we have these, and then we have the D types. Of course, we have the df.x. So we have been able to drop as in we have been able to drop two features. All right, so we have been able to drop resting BP and resting ECG. All right, so that we'll be able to have a better performance, and of course enhance interpretability, reduce overfitting, and of course to improve the model efficiency. And that's what we've actually been able to drop here. All right, and of course we can actually lead that, if it is actually not, but like I said, we dropped our own. And then now we're going to be talking about train, test, and splitting and scaling. Of course, scaling and standardization are actually very important. Standardization means that we are converting our data set into numeric features, and then we are saying that the mean is going to have the mean of 0 and the standard deviation of 1. And of course, scaling is a process by which we actually try to make sure that our data sets are not too distant in terms of maybe having a particular one having 0 and the other one having 10. All right. If you have data set and you, for example, if you're dealing with deep learning algorithm, you can actually do that by dividing all of them by 255. All right, in the matrix. All right, because you want to make sure that each of the values is between zeros and ones, and this helps you to be able to have a very good performance of the model. All right, so we're going to be splitting our data set into x and y. X, we dropped our disease here, which is the target or variable. So here, this is the x, and as you can see, we're going to drop only the art disease future or the column. And of course, this is axis is equal to 1 because we're going to be talking about the columns and not the rows. So that is why we have axis equal to 1. So we're going to drop only the art disease, and this S is going to contain all the training data, and this Y is going to be for the art disease alone, while this X is going to be for every other features apart from the art disease. The X test, the Y train, and the Y test, and then we are going to be using we're going to be dividing the train data into two 80%, all right, for the train, and then the test is going to be 20%, and the random is 5, then stratified. Of course, we are trying to like see here this X train dot shape and Y train dot shape. All right, these are the YX train dot shape, and these are the Y train dot shape. All right, and then we've been able to see here. All right, this is df dot value count. This is data frame for heart disease, and we notice that the people that have the samples that have heart disease is 508, and the samples that don't have heart disease is 410. Now, this actually tells us that we have somehow a balanced data set. All right, because if this is not balanced, then we are probably going to have to do what is called the oversampling or the undersampling. All right, because by the time we train this model, and one of these zeros and ones are actually significantly different from each other, like probably maybe you have 200 or something to 600 or something. We have to do or oversampling or on a sampling so that we'll be able to have a balanced data set. And this will, if we don't have a balanced data set, or if we don't have a balanced target variable, it will actually adversely affect the model. And of course, you'll be discovering that it's going to be predicting, the model is going to be predicting the one that have the larger share of that has a larger number. And of course, it will affect the model, and it will not be able to predict a very good result. So now we are trying to now here we are doing the standardization, and then we are doing the scaling. Now this scaled data, which is x text x train scaled. All right, this is x this is x text scaled, and of course we have the x train scaled as well, x train scaled. So we're going to pass this scaled into our dataset. First, we're going to be talking about logistic algorithm, logistic regression. Now, under this logistic regression, we're going to and the same thing we're going to be doing for every of the models, the 7 models that we're going to be using. Now, we're going to do this random seeding for reproducibility of a model, such that when you have this model run different times, it's going to give us the same results, right? And then we are going to define hyperparameters for this logistic regression. Of course, you can actually get more information from documentations of logistic regression on your website to be able to know the latest ones. So we've been able to get the parameters for this model, and then of course we're using GridSearchCV. All right, we're using GridSearchCV to be able to see and k-fold cross validation. All right, which is actually very, very effective in terms of what we are trying to do is that we're trying to optimize our model to be able to get the best results. So we're going to use this GridSearchCV and k-fold cross validation to be able to tune on our parameter model to be able to get the best hyperparameter. All right, possible, the best parameter possible from this logistic regression algorithm. And the same thing we're actually doing. And of course, we're going to pass. After doing that, we're going to fit this data into our train scaled model. And of course, this is the future. This is the future, the future names, which we've actually been able to do here. Now, evaluating the model, and then we are going to, of course, calculate the AOC ROC curve, And of course, we in this dataset we're going to be also be doing the classification report, which is here, and then this is the plotting AOC ROC. And after running this model, of course, we've been able to get here. We have this is the this is what is called confusion matrix. All right, confusion matrix is actually very important in terms of getting the information from our data set. And of course, we have uh, we have the confusion matrix here. We have the true positive, we have the false positive, we have the true negative, and we have the false negative. So it is actually very imperative for us to be able to understand some things about these informations: the true positive, the false positive, the true negative, the false negative. And of course, we can see here. Now, this is the true positive, and this is the false positive. Now, this is the false negative, and this is the true negative, like we can actually see on our data set. Now, this true positive meaning the model correctly predicts the presence of heart disease. Example, if a patient actually has heart disease and the model predicts that the patient has heart disease, this is a true positive. And of course, this is the false positive, which means that the model incorrectly predicts presence of. So what we actually after are all about, what we after is true positive. Now, now, it is actually very imperative for us to be able to know something. Now, what we want to do here is that we want to predict the presence of heart disease in a client. Now, when you're talking about when somebody has a positive result in terms of predictions, you know that that means that the person has heart disease, and of course, we want to be able to ensure that we have the highest rate of true positive, and that is why we are actually trying to develop this algorithm, right, to be able to give us the highest rate of true positive, among the clients. So we want to be able to say that okay, fine, out of 100 people, all right, that out of 100 samples that we run in that we train our data in, all right, about 99.9% of them actually have true positive, which is 99 is true positive. And so this will be able to enable us to be able to predict with high degree of accuracy that this particular client has true positive. And of course, we cannot just actually take that like that. No, we have to also go to the domain experts because it is actually very imperative for us to be able to to have a good relationship between between the algorithm in terms of the result and also the domain expert. The domain expert will be able to validate most of the things that because we need to be able to ensure that we have good and very informed decisions in terms of our prediction. So, of course, we can actually try to say that what we actually after right now is the true positive, meaning that the model correctly predicts the presence of heart disease. And when the model predicts the presence of heart disease, that is what we are actually after. So we are actually trying to make sure that the true positive actually very significantly high and is actually more than the true negative and every other and more than the false negative. So we want to ensure that, for example, this is false positive means that the model incorrectly predicts the presence of heart disease. So we want to ensure that the true positive is actually very much more higher than the false positive, and that is what we are actually trying to do here. Now, of course, in each of the 7 models that we have been able to run, all right, we are trying to create what is called the feature importance, and the feature importance is actually very imperative. For example, you can see that the feature importance is a technique used in machine learning to understand the relative importance of each feature or input variable in predicting the target variable. It helps to identify which features have the most influence in the model's predictions. Coefficients in linear models. In linear models like logistic regression, the coefficients associated with each feature provide information about their importance. Features with larger coefficients have a greater impact on the model's prediction. So it is actually very important for us to be able to explain to stakeholders that this particular feature has the highest importance in terms of predicting the end result or maybe the target variable. And if the stakeholders could actually try to invest significantly or look significantly in those features that have significant impact on the target variable. And of course, this can actually be able to help businesses to be able to know the future that they need to invest in or that they need to drop in terms of making decisions that affect their business's interests. So we can see here that the ST slope has significant impact in terms of this model in terms of predicting the end result of this model than every other ones. Of course, the next one is exercise algebra, and of course, these are the ones that actually have significant impact in predicting the result of these. So when you have these ST slope, you can actually know that it's you can actually conclude probably technically with very good information that these now of course we have Bernoulli Naive Bayes also. The same thing was also done on Bernoulli Naive Bayes, defining the random seed for reproducibility, and then we generate a few parameters for Bernoulli algorithm for Bernoulli Naive Bayes, and of course we have we use GridSearchCV and K-fold cross validation to be able to tune our hyperparameter model to be able to get the best hyperparameters for our, and then we feed them into this model, and of course we train them, and then we are able to get the results. We're able to get accuracy, and we're able to get these precision, the F1 score, and the support. Now, depending on whichever one you want, but basically in this model, I would prefer that we go for the recall, all right, because it actually has a significant impact in terms of this model. Of course, this is the confusion matrix, like I said, and of course, this is the AOC ROC, and we have an 89% accuracy here. And of course, this is the feature importance for Bernoulli Naive Bayes, and this is the same thing that was done on every other models. All right, this is LightGBM, and of course, the best one, the model that actually produced the best result in terms of the performance is actually categorical boost classifier, which is a decision tree based model. And of course, this is the random seeding, and this is the hyperparameter models. All right, this model was trained we use GridSearchCV and K-fold cross validation to train the to tune the hyperparameter models, and of course we are able to get this result here. So we have this one actually gives us a 92% accuracy, and of course this tells us that we have 63. All right, this is a 63 in terms of the true positives. All right, and then we have the false negative, which is 6, which is actually very significantly higher than every other one. So we can actually say conclusively. Of course, we're not going to see anything here, but we're going to go forward. SVM2 was actually used. Of course, we can actually check through these codes and of course replicate them. And of course, the codes will definitely also be dropped much later. All right, under these videos. Then of course we have SVM support vector machine was also used to train this same model, and we got a very good result. But like I said, all these models are optimized, and of course we have the feature importance for these, and of course we have the random forest. Random forest was also used. All right, and of course we have multi-layer perceptron classifier, which is a deep learning algorithm, was also used to train our model. And of course we have this model, which is 50. This is the hidden layer, and we use ReLU, we use alpha, and then this is a these are the things that we used in terms of MLP, and of course we have the same thing, the report support, the classification report, and the AOC ROC, which is 90%, and then the feature importance. This also tells me that we have the old peak. Old peak actually has a significant impact in terms of the predictions of this model, and the ST slope is the second. All right, and then of course we are trying to tabulate the scores for each of these models. All right, we're trying to get the scores for them. So we define, this is a report, we define the model, the accuracy, the F1 score, the precision, the recall, and the AOC ROC. And that is what we actually did here to be able to get in terms of the tabulation. We have been able to tabulate it, and of course this is the result. We can see here that we have the logistic regression. This is the accuracy, and this is the categorical boost classifier. This is the recall. Recall is 86%, and then the AOC ROC is 91%. But the one that has the highest recall is actually multilayer perceptron classifier. So if we are going to be using the recall as our main as our main result, all right, metrics, like I said, they were going to actually have to give a multi-layer perceptron classifier as the best performance model, which actually has 89% in terms of the recall. However, if we're going to be using ROC AUC, you have to give it to a categorical boost classifier. So it depends on what actually individual wants. But if we are actually going to be talking about recall, the best performance mode in terms of this recall is going to be multi-layer perceptron classifier. All right, and of course, this compare the scores of this model in the chart after optimization. After it has been optimized, we decide to do the chart, and then we can see here this is the model performance in terms of the AOC, ROC. So we can see here 91% for the categorical boosting classifier. Like I said, it depends on what you're actually trying to do, and of course, this is the chart on a test data set. And then, of course, we're trying to also try to explain. It's very imperative for us to be able to explain to stakeholders, to people, to business owners, right, in terms of the artificial intelligence, the result of artificial intelligence. And this is actually why we have decided to install the SHAP. All right, SHAP is actually one of the is a SHAP, which is Shapley Additive explanations, is a method used to explain the output of machine learning models by quantifying the contribution of each feature to models' predictions. Right? It leverages game theory concepts to assign a value to each feature, indicating its impact in the model's output. All right, so this is a SHAP. SHAP is the more suitable for tree-based models like XGBoost and categorical classifier. So we have to use two of them. And of course, this is it. We can see here that this SHAP ST slope actually has significant impact in terms of the predictions of our models. And basically, this is LightGBM Classifier, which is also a decision tree based model. And also, it's telling us that ST slope also has a significant, which is like 1.2, close to 1.2 in terms of in terms of this. And then, of course, we can go here and we can see here that this in terms of the main SHAP value, average impact on model output magnitude. You can see here also here that ST slope has more than 1.2, more than 1.0, and this, of course, this is also the light tree based classifier, almost 1.2 was actually given to us here. Then we are actually trying to see we can design and implementation of models through user interface. And of course, we've been able to say df.columns. This is df.columns. These are the columns that we are actually talking about after we have removed two columns. Remember, because we don't want to we want to better the performance of our models. And of course, we've been able to do some things. This is the LR model. This is the model name for light, and then we define these models, and then we now create checkboxes. All right, and then we create a prediction button, and of course we define this class, which is we have a predict button clicked, and then we try to run this model here. So it's actually giving us this. So for example, we have logistic regression. We can actually populate this 0 and 1 and click on predict, and it's going to tell us that the predictions logistic regression is 1. And then we can go to categorical boosting classifier, or let me say random forest, and then we can say let's predict again. Predict, we have 1. So it tells us that this particular person actually has a heart disease, which is 1. All right, then of course we can actually try to also create a streamlit from this. We can say pip install streamlit. All right, streamlit is actually one of the very good library or software that we can use to actually display the machine learning algorithms or deep learning algorithms. So now we've been able to create run at artdisease.app.py, and this is the artdisease.app._app.py that we are actually, of course, this particular one is also on the directory that we are running this one at the same time with. So we have to actually make sure that this is actually in the directory, and then we've been able to define using CSS and to be able to, this is the st.mark. You can actually get a lot from these streamlits by going to the streamlit documentations. All right, the streamlit documentation actually contains a lot of what you can actually use to create. We also have beautiful template that you can use, to generate your to be able to do your to create your user interface for your machine learning algorithm. And of course, it actually contains a lot of things. Going to Streamlit documentations will actually help you to quickly deploy your algorithm. So these are the codes that we have actually been able to use. And by the time you come to this place and you run this app, all right, you run this app, it's going to open the browser for you so that you'll be able to visualize what you've been able to do. All right, so it's actually very imperative. Running this thing is important for us to be able to go to their visualizations, and then it's actually opening right now and it's running. Okay, so we're going to wait a little bit while it runs. All right, and like I said, it's actually not that difficult by just going to the documentations of Streamlit. All right, you can be able to get some already created applications that has defined pattern or defined models there. So of course you can see here that we have this is the sidebar. All right, this is the sidebar that we have created. You know, in this sidebar we have this is the options. You can choose options between these models, support vector machine, and then or random forest, and then you can populate this and then you can run it. All right, but like I said, I'm going to put everything at zero. This is the model information. So this is the tab. All right, from here you can see here that we have a tab. We have the visualization tab. Now, this visualization tab contains pictures, graphs that I've been able to do here. All right, you can see many of these items, many of these visualizations, very beautiful. They are the ones that I actually include in under these visualizations. If you go down, if you scroll down, you can see them here. All right, these are the visualizations that I was using my data set. And of course, if you want to change these to, you can go to settings and then you can change. If you don't like the white, you can go to light. So you can go to light, and then you see here. But basically I actually like the black or the dark theme, so I'm going to go to dark and it's going to show me dark. This show dark. So of course these are let me just click on these Bernoulli Naive Bayes, and then let me go to this place, and of course maybe probably populate this data, or you can say 0.15, and then male. You can change this to female if you want, and then you can change your parameters here as well to maybe 1 or 0 point something, or type it 1.25, and then you can just go to predict. All right, and then you can see here that this based on these features are provided there, this particular information, this particular features using Bernoulli Naive Bayes that I've actually been able to use. You can see here that after clicking on predicting, it tells me that there is no heart disease, and of course the probability of this no heart disease is 0.42. But sometimes you can actually see as high as 0.98 to tell you that this particular one doesn't have heart disease. So, of course, these are the things that we are actually going to be doing today. So, basically, if you have any questions, you can actually ask, and then probably I'm going to be able to, take time to be able to answer. All right. So, like I said, this is actually one of the ways by which you can use to predict the possibility that a sample has heart disease or doesn't have heart disease. So, thank you for listening, and see you in another tutorial. Bye.